Okay, now we are going to talk about what are called Bronsted-Lowery acids and bases. This is a bit more comprehensive of a definition of acids and bases and is the one that we will be using during this class. Okay, because it encompasses all of the acids and bases that we're going to come into contact with. So acids are pretty much the same. They're going to focus on that H plus that they can give off. So the Bronsted-Lowery theory really just focuses on that H plus in general. So this focuses on H plus transfer. Okay, so it's like a little bit broader of a definition. So we call an acid is a substance that donates H plus, or we might say donates a proton, okay, because H plus is really just a proton because it's lost its electron. Right. A base, on the other hand, is not necessarily OH minus. OH minus is a base, but we're going to expand that definition to a substance that accepts that H plus proton. Okay, so OH minus is a really good base because H plus connects to the OH minus and you end up with a water. Okay, so this is our more expanded definition. Expanded definition. I'm just going to write that. Okay. So the other thing I want to talk about is what happens when you have H plus in water. We make what's called the hydronium ion. You guys are going to see this a lot. Essentially, H plus is really, really unstable. If it's floating around by itself, it's going to connect to a water and make hydronium. So we're going to see a lot of that in our solutions. Okay, so what happens when you put HCl in water, essentially, right? I've got HCl, which is hydrochloric acid. If I put it in water, we know it breaks into H plus and Cl minus aqueous. But I said, in reality, this guy here is really, really, really unstable. So what it actually does is you don't have a free proton. No free proton. It actually connects to a water. So since we write this as the dissociation equation, but in reality, HCl in water makes H3O plus and Cl minus. Okay, so that's kind of what this picture over here is showing. You've got HCl. Goes into water. We know it completely dissociates because it's a strong acid. The H plus actually connects to a water molecule. So in reality, this is what's in there, not just H plus. Okay. So we, like I said, we'll see a lot of that. So what I'm going to show you is an example of a neutralization or an acid-base reaction that is a Bronsted-Lowery reaction. And I'm not going to use OH minus. I'm going to actually use something else that is a base under the Bronsted-Lowery definition, but not under the Arrhenius definition. So that would be ammonia, okay, NH3. Okay, this is a base. It's a weak base, but it is a base, and it's a Bronsted-Lowery base. So if I react that with HCl, which is an acid, okay, by definition, the acid donates the H plus, and it's going to go to the base. So then my products are Cl minus because it has lost its hydrogen, and NH4 plus because it has gained that hydrogen. So now this got donated, I end up with this, and that's actually what's in the solution. Okay, so this is an example of a Bronsted-Lowery acid-base reaction. Okay, so like I said, we use this Bronsted-Lowery definition. And we are going to start talking about acid-base equilibrium in regards to Bronsted-Lowery acids and bases. So there's that equilibrium word. I told you this whole semester is really based on equilibrium reactions, things that can go back and forth. Okay. So if we're looking at acid-base equilibrium, these are really what happens when you have a weak acid or a weak base. So in equilibrium reactions, most of these are going to be weak electrolytes. Okay, and when I say weak electrolytes, what that means is that they only partially dissociate. Okay, so we've talked about this before in 161, but weak acids and bases partially dissociate. So that makes them weak electrolytes, which means instead of having a complete forward reaction, we're actually going to have an equilibrium going on. Okay. So what happens is this, right? This is our weak base. Okay. We know this is not one of those strong bases that you have to have memorized. It is going to gain that H plus when you put it in water. So when you put this in water, notice I'm doing my equilibrium arrow, not just my forward arrow. I end up with NH4 plus aqueous and OH minus aqueous. Okay, however, when I put a weak acid, and I know this is a weak acid because it's not one of the 6 that I had to have memorized, essentially it's going to donate its H plus, so we end up with F minus and H3O plus. Yes. Okay. So you really got to look at where that H is going, if it's an acid or if it's a base. Notice on the products side, I end up with OH minus and H3O plus. OH minus, super basic. H3O plus, super acidic. So that's kind of how everything relates together. We're going to start looking more at acid-base reactions here in the next one.